Good morning, everyone. My name is Manoj. My office is at South Campus, DISAOE, Akraham, A122. These are my contact details. As the picture suggests, I'm a experimentalist. I use lasers to do my experiments. In the coming 5 to 10 minutes, I'll detail what are the activities I'll do and what you will be learning if you join the laboratory. First, let me welcome you to begin a new journey where the right questions matter far more than answers. In research, you don't just observe facts, you create them. Every challenge we take on is an opportunity to push the limits of what's known and shape the future. My own work spans solution from the dustbin to the moon, literally, where curiosity meets real world impact. If you are ready to question deeply, think broadly, and persevere through uncertainty, you will discover that this is more than a research, it's an adventure into spectroscopy and machine learning. So broadly, this is what I do. I use lasers to collect spectroscopic signals and use those signals to solve real world problems through machine learning. There are two spectroscopic techniques: Raman spectroscopy, which everybody knows, laser induced background spectroscopy, which is by far the new one, which doesn't come in textbooks. This is still in the lab level research. There are some instruments which have come out, but the whole research is pushing towards that, how to make or push the borders from LIPS being a laboratory tool to a tool which is available to everyone. Machine learning, we use various techniques, including artificial neural networks. So what you will be learning, you will be mastering cutting edge laser and spectroscopic techniques as a PhD scholar. So these are the tasks or skills you will develop after the completion of PhD. The first and foremost being steering the laser beam, that is known as alignment, taking the laser from one point to the other wherever it is required, measuring the laser properties like laser spot size, intensity, wavelength, rep rate, using different kinds of instruments like oscilloscope, power meter, and various other things, and then use all this to collect the data which matters at the end. Not only collect, gather, organize, and take decisions using the data. And finally, designing a telescope where a signal from a far off point, 50 meters, 100 meters, can be collected using lasers. That's going to be exciting. You'll not only learn those things, you'll learn these things: Python programming, which will be used for both machine learning and interfacing instruments; machine learning, which will be used heavily for data analysis and model building; interfacing the instruments with Python and LabVIEW. LabVIEW is a commercial software and which is widely used world over. Now Python is picking up, so if you join, you will be changing the code from LabVIEW to Python, and web app development to make our workflow into available to everyone as part of open science. So these are not just for your PhD, but this can boost your career opportunities as well. So let's see this video. What it shows is a lens. When it focuses the light, it looks like this, and this is known as the plume. And if you put a spectrometer, that becomes the spectroscopic signal, and you will see something like this: wavelength in the visible region and intensity in arbitrary counts. So each peak, sharp peak, corresponds to an atom or a combined atoms in the plume. As you can see, carbon, hydrogen, nitrogen, and oxygen. So this is like a fingerprint of the materials, and many of the projects which I do are dependent on data. Hence, I will use machine learning. This is a typical laboratory setup. This is the lens and it is focused. And a similar experiment is done by Professor Prem Kiran, who uses interferometry and shadowgraphy, which he will tell in your talk or he has already told you. Let us quickly go through some of the lip spectrum of different materials. This is for human tooth. You can see calcium, magnesium, both male and female. Again, 400 to 800 nanometers, heavily calcium, hydrogen, sodium. So this we're trying to see. One paper we have published on whether we can make a decision on whether a given tooth is male or female based on such spectra. There are many other aspects which are looking for, another being the age. Lip spectrum of tungsten, which is more of a fundamental study, wavelength versus intensity, and as a function of distance. This can be used for elemental analysis, where we have published a recent paper which cuts down the time by 70 to 80% on getting the elemental analysis using the lip spectrum. There are a lot of other things which needs to be fixed before the technique is established, and lip spectra of various other materials. Now, what do you do if there are many materials whose spectrum looks similar? So that's why we use different data analysis. Don't bother what it is, but it goes through different data analysis, and then we can cluster them and take a decision. And if it becomes difficult, then we use machine learning. I hope these terms are now in the terminology of everyone: supervised learning, regression, unsupervised learning. Even if you don't know, it's don't worry. This is a matter of one semester, and you will be having a good understanding to implement it to spectroscopic data or any other data. This is a typical workflow of the entire experiment. First, you have different samples. What here I'm showing is the plastics. They use the laser, focus it onto the material, you will get different spectrum and perform different machine learnings like principal component analysis, artificial neural networks, which leads to the identification of plastics. This is a big deal as far as plastics segregation of the uh, plastic segregation from the dustbin is concerned, because there are a lot of plastics which is already collected, and people are looking for quick solutions to segregate them so that recycling becomes easier. So this is a result of a typical study which leads to classification accuracy. This is using artificial neural networks. And let me summarize at the end by showing some of our recent works. This is appeared in Optics Express. This we termed as slice, which can give concentration of a different elements present in a material with 70 to 80% reduction in time and efforts compared to present efforts. Now, this is one of the web apps which is published again, which aims to uh, bring the workflow in form of GUIs and accessible to everyone, so that the job becomes very easy, and the time saved here can be used for something else. This is another GUI which is under development, and probably if you're joining, this is the first thing you'll be working on, and quickly it is going to publication. And there's another work on Raman spectroscopy, where we are using machine learning for quantification of explosives in mixtures. And at the end, these are the projects which will be coming in the next 3 to 5 years. The things which are at the bottom are presently going on. Lips for Chandrayaan, we are working on some lookalike materials. There's a project from ISRO, and we'll be developing a GUI. Here I'm a co-PI. Entire GUI will be developed for the elemental analysis and concentration finding, and will be given to ISRO. Plastic segregation, which I've already discussed, elemental analysis, the slice technique, which I've discussed. The top three are the projects and in the pipeline. Noise reduction, this is already submitted to DRDO. This aims to improve the Raman spectroscopy capability by dealing with the noise. Additional questions could be like, what is the noise level beyond which classification goes bad, or how to take care of the noise. Development of a standoff system. This is the first image which I have shown. Presently, we have a lab system, but there's a lot of interest in making that system into a one unit. So we are writing a project on that. And finally, this is under 5 temperature measurement. There's a challenging thing under DRDO project under proposal, where we have to find the temperature of a fire at a distance of couple of kilometers. And the challenge here is the event lasts for about 200 milliseconds, and within the 200 milliseconds we have to measure the temperature about 20 to 30 times. So welcome on board to spectroscopy and machine learning. If you have any questions or doubts, please feel free to call me. Thank you.